Hello, my name is Tommy, and in this video I'm going to talk about the theory and practice of strength training programming. This is an intermediate or advanced video, which means that I assume that you have decent knowledge of math, at least high school math, preferably some math in university perhaps, and I also assume that you've been training for some time. I'm going to talk about how I have used mathematical models to plan my strength training. I'll talk about long-term progress, volume and intensity, and repetition schemes, and how mathematics can be used to find good strength training programs that you can use for long-term planning. All these ideas are implemented in a Python package. Python is a programming language. It's called streprogen, and it stands for Strength Program Generator. I've been training since 2005. Not the strongest person out there, but I'm decently strong. Did some powerlifting, broke some records in my youth, and I've been using mathematics to model my strength training since 2013. Not 1013 as it says in the presentation. And I've included a picture of myself just to show, because this is going to feel a bit theoretical, so I just wanted to show with a picture that, I actually do go to the gym. So that's why I included a picture of myself. Let's start with long-term progression. And the first thing that we have to agree on is how the rate of adaptation, what it looks like for an athlete in strength training in particular. So the law of diminishing returns states that as you adapt to something, your rate of adaptation will slow down. This can be formalized with a differential equation, which says that if S is strength, the rate of change of strength is proportional to the difference between genetic potential, GP, and your current strength level. So what this means is that if you're far away from your genetic potential, you'll have good gains. You'll progress quickly. You'll adapt quickly, and you'll get stronger quickly. If you're close to your genetic potential, progress is going to be much, much more slow, right? So in this graph, I show you 10 years and an athlete starting perhaps with 50 kilos in bench press. And maybe his genetic potential is 180 kilograms. And this shows how according to this differential equation, the law of diminishing returns, how his progress will look over 10 years. Of course, we don't really know what someone's genetic potential is until they've trained for a while, and we don't know how quickly they'll adapt. You could do studies, of course, and measure this and find out what K is and what the GP is and so forth. But for our purposes now, this is just a mathematical model, and we take this to be true. This is how people adapt to strength training. Even though we don't know K, the rate of adaptation, and we don't know GP, the genetic potential for a specific athlete. Okay, so how can we use this to make not 10-year plans, but maybe half-a-year plans? Well, we need to be able to force the function to go through endpoints. So for instance, here we have an athlete who starts at 50 kilograms in the bench press, and within 12 weeks, he or she would like to progress to 70 kilograms. So if we take that differential equation that we saw on the previous slide and we solve it, and we add a linear function to it to force it to go through this second endpoint here at 12 weeks and 70 kilograms, we get this equation. So this is just algebra. You just solve the differential equation and you do the algebra and you get this. And what's nice about this is that if you put K equals to 0, you have linear progress. That's the first thing that you would think of if you want to get from 50 kilograms to 70 kilograms in 12 weeks. Linear progress is the first thing that you would think of, right? If you want to accommodate the law of diminishing returns to some extent, then you can set K equals 1 or 2, and that means that you'll adapt more quickly initially and your rate of adaptation will taper off. So what should you put K equals to? Well, it depends. It depends on the time frame, and it depends on the experience of the athlete. Usually I put it equal to somewhere between 0 and 2 for me and the people I set up programs for. So that's usually a good parameter. But the point of this is that we can use it to plan strength increase in programs, either linearly or accommodating the law of diminishing returns. If you've been training for a while, you might want to add some periodization. So if you just started training, you can more or less add some weight, maybe half a kilo or a kilo, every single time you go to the gym, because you adapt so quickly. So then you should not use this periodization scheme. You should just linearly increase the weight. But as you become more advanced, you'll notice that you can't really push yourself every single time you hit the gym. So then you might want to do something like this. This is a sawtooth periodization, meaning it goes up and then drops down. And this is a 2 steps forward, 1 step back periodization scheme. It's, again, one of the simplest things that you would think of. And you can change K here. You can have it equal to 0 for a linear progress, or you can set it equal to 2, for instance. All right. This can also apply to volume and intensity, by the way. It's not necessarily just the actual kilos that you lift. We'll get back to that soon. And the way you compute this, you just multiply the original strength function that we saw on the previous slide by a sawtooth function. And this is implemented in my software package. Of course, for a person going from 50 to 70 kilograms, you would not do this. You would just use a linear progression scheme. You can change the period of the periodization. One of them is just 1 forward, 1 back, 1 forward, 1 back. That's the blue one, period 2. 2 steps forward, 1 steps back. That's period 3. 3 steps forward, 1 step back. That's period 4. In general, the higher the period, the more advanced of an athlete you are. You can also change the scale, these functions. I don't have any strong opinions about that parameter choice, and I don't want to talk too much about parameter choices in this presentation in general, because it depends so much on the individual. This is what long-term modeling might look like. Here's half a year and a concrete plan for someone to increase from 50 to 70 kilograms in the bench press, for instance. K equals 1, so there's a slight non-linearity. The period is 3, which is the 2 steps forward, 1 step back scheme, and the scale is set to 0.025 here. The sawtooth is not the only option. You could also use a sinusoid, for instance, to do periodization. So here is the same person going from 50 to 70 kilograms in 24 weeks, and it just shows you a couple of sine waves. I prefer the sine wave was my first idea, but now I prefer the sawtooth. I don't really use this anymore in my programs, but it's nice to have the option to use it. That concludes the first part of the presentation. Next, I would like to talk about repetitions and intensity. So we're going to assume that there exists a relationship, a function between repetitions and intensity. And the intensity of a set here is just the percentage of your maximum 1 RM. So by definition, 1 repetition maps to 100% of your 1 RM, or just your maximum, right? So if you decide that you want to do 1 repetition, it has to be your maximum. So what's 2 repetitions? or 3 repetitions. 2 repetitions is usually just above 95% of your 1 RM, usually. 4 repetitions, as you can see on this graph, is usually around 90%, perhaps a bit less, perhaps a bit more, of your maximum. Now, this varies a lot, and this is just a mathematical convenience because we have to establish some relationship between these parameters. But this depends on your gender, depends on the specific exercise, and it depends on the individual person. So this is not set in stone at all. Here's an example. Let's use the normal relationship, the blue one. If John has 120 kilograms as his maximum, 5 repetitions using this normal relationship, sorry, my phone rang. 5 repetitions with a normal relationship means doing approximately, lifting approximately 105 kilograms. The tight one looks more like what female athletes might have as their relationship, and the relaxed one is just even more extreme in the sense that it will make your 1 RM heavier compared to doing many repetitions. This doesn't have to hold for, we're just using this for programming, not for prediction of 1 RM. There's a difference. If you wanted to accurately predict your 1 RM, then this is, it's the best you can do without actually doing your 1 RM. But we're just using this to create strength training programs. And if you're a bit off there, it doesn't really matter because you shouldn't go that heavy all the time anyway. That's it for this part for now. Just remember that there exists a relationship between repetitions and intensity for a single set, and it's given by a mapping that looks a bit like this. Next up, volume and intensity. By volume and intensity, I mean volume and intensity across sets in one exercise. And my definition of volume and intensity for the purposes of this presentation is given by these equations. So the volume is the total repetitions. For instance, if you do 5 repetitions, then 4 and then 3, 12 is your volume, because 5 plus 4 plus 3 equals 12. The intensity is the average intensity across the individual sets. So you do a 5, and that maps to an intensity by the function that we just saw 2 slides ago. And your 4 and your 3 likewise map to an intensity. And then you do a weighted average over those 3 intensities, where you weigh them by the repetitions. So that's this equation that you see. And there's a typical thing that people do. You start off your maybe 12-week program or 8-week program with high volume and low intensity. So maybe you're doing 8 repetitions or something like that. And then as your program progresses, you decrease the volume and increase the intensity. So by then, maybe you're doing sets of 3 or something. So you go from 8 to 3. And this is an old idea, and what a lot of good, simple programs use as their main periodization. And this is periodization because if you stack these programs consecutively after one another, you see that there's an implicit sawtooth periodization of volume and intensity. So that means that consecutively doing these programs actually reduces to the sawtooth function that we saw earlier for weights. So you can use that sawtooth function to plan your volume and intensity as well and do periodization of those 2 program parameters. Okay, that's nice to know. It also means that you don't have to do periodization across the entire program. You don't have to linearly increase or decrease across the entire program. You could do something like this. So this is half a year of planning for an athlete. And we do a long-term linear trend where we decrease volume and increase intensity, but we also do this periodic component, or where we construct it so that when the intensity is at its highest in these short periods, the volume is at its lowest. So you could do something like this. Okay, and again, I don't want to talk too much about parameters like how much should volume increase, what should the period be for these functions. Just know that this is possible, and a parameter choice, I don't want to make any individual recommendations. Something like this is probably sensible for a lot of people, a lot of athletes, but I don't want to get into that because it's a whole different concept what specifically every parameter should be. Lastly, I want to talk about repetition schemes. This is important. This is what kind of ties it all together. We'll see how we can formulate repetition schemes as a mathematical optimization problem and find optimal repetition schemes. And we'll use that along with all the other concepts to create an optimal training program given that our parameter selection is good. Okay, so let's assume that you want to do sets of repetitions between 2 and 5. And you want to create schemes which have a volume of 12, so 12 repetitions in total. How many ways can you do this? It turns out there are exactly 12 ways to do this. And they are listed, okay, this is 10. So there's a mistake here. I think I either excluded 2 of those 12, or there are actually just 10 ways of doing it. So there's an error here somewhere. But looking quickly, we can see that this does sum to 12 repetitions in every single repetition scheme that you see. So each one of these 10 tuples listed are repetition schemes. And you can verify that each of them only use sets in the range 2 to 5, and that they all sum to 12, and that they're all decreasing. That's another property that I impose on these repetition schemes. So you can't increase, you can't go from a single repetition or something to doing 8 repetitions, but you can go down and go heavier across your sets. Okay, let's look at a slightly more advanced example. What if we allow repetitions in the range 3 to 8, and we want to create schemes with 25 repetitions in total? It turns out that there are 45 ways of doing this, and some of these are listed below. I want to draw your attention to 2 of these marked in bold, and I want to suggest that they are problematic for 2 different reasons. The first one, the one that says 88333, is problematic because it has a large jump. You go from 8 to 3, which means going from pretty low intensity to a very high intensity. And this might correspond to a large jump in weights, which you don't necessarily want to do. It would be more comfortable to do a set of 5 in between here, for instance. The problem with the second one is that it has 5 different sets with 5 different repetitions, and therefore 5 different weights. So you have to change plates a lot. If you want to do this scheme, it would map each of those repetitions in 7, 6, 5, 4, 3 would map to different weights, and you would have to run back and forth with a lot of weights. So if you have 45 to choose among, you wouldn't choose one of these 2. You would choose some other ones, I hope. I hope you agree with me. But this is an opinion, of course. Okay, let's constrain the possibilities. If we add 2 constraints to the previous problem. Constraint 1, the max difference in repetitions is equal to 1 for adjacent sets. That means you can never go from a 5 to a 3, for instance, because then the maximum difference would be 2. So you can only decrease by 1 in 2 adjacent sets at most. So that's the first constraint. The second constraint, the max number of unique sets in the scheme is equal to 3. So you can do a 5, 4, 4, 3. Even though it has 4 sets, the number of unique sets in 5, 4, 4, 3 is still 3. If you add these two constraints, it reduces the number of schemes that are allowed. So there was 45 schemes allowed in total without these constraints. That's what we learned in this previous slide. And if we add these two constraints to remove the bad repetition schemes, we're left with, 11 in total. Okay, so what's the difference between these 11? It's the intensities, and I've marked these in square brackets after the repetition schemes. So depending on what intensity you want to accomplish for a given exercise in a given week, you would pick one of these. Of course, you can't really have a very high or very low intensity because we've constrained the sets to be between 3 and 8 repetitions. So if you want to go a lot higher or a lot lower, you might have to look at those constraints as well. Okay, let's turn this around a little bit and formulate it as an optimization problem. Okay. If sets of 3 to 8 repetitions are allowed, how close to 25 reps and 85 intensity can we get subject to those two constraints on the maximum difference of repetitions and the maximum number of unique sets? That's this optimization problem. If S is a repetition scheme, we want to find the argument in the set of allowed repetition schemes that minimizes this sum of squares. So you have an error, the intensity minus 85, and you have an error, the repetitions minus 25. And those two errors, you square them and add them. And the optimal solution then is 6, 6, 5, 5, 4 for this optimization problem. This kind of optimization problem is called a mixed integer quadratic program. And the way that I solve this in my software package is I enumerate the search space. I use a tree search algorithm and I do pruning of that search, which is very efficient, and works excellent for problems like this. So this optimal repetition scheme, it gives us an intensity of 85.9 and using 26 repetitions. And that's fairly close to 85 and 25. If we relax or just completely remove these hard constraints on the maximum difference in repetitions and the maximum number of unique sets, we'll find this optimal repetition scheme, which is spot on in both intensity and repetitions, but it uses more than 3 unique sets, and it has a max difference of 2, as you can see, going from 8 to 6 and 6 to 4. All right. The search space is quite big for these problems. It's bigger than what you would want to do by hand. So you don't want to sit and do this by hand. If you allow sets of 1 through 8 and you look at all the ways of creating sets with less than or equal to 20 repetitions, there are 13,000 ways of doing this. So it means you need a computer. Even if you do impose those two constraints, you're still left with 855 ways of doing it. But if you write the software correctly and you formalize it using tree search and you prune that search, you can do this in milliseconds on a computer. And that's kind of what it's one of the things that my software implementation does. So let's talk about that a little bit. This is the practical part of the presentation. Okay, so let's talk about streprogen, the strength program generator, my practical implementation of all these mathematical ideas. You define the duration of the program in weeks, how many days you want to go to the gym, whatever exercises you want to do, the weights, the intensity, and the volume, and so forth. The intensity and volume, you can, for those two parameters, you can use your own custom-made periodization functions. And then streprogen will loop through every week, every day, every exercise, and it will solve that optimization problem, and it will give you the optimal repetition scheme in return. So there are good default parameters, or you can, to your heart's content, change this up and use whatever you like. The software is completely agnostic to your specific programming methodology, whether you like doing split programs or full body or whatever you think about periodization, you can do it. It's more of a toolbox than a ready to go template or anything like that. You have to think a little bit, and even though it gives you default parameters, you have to think about the parameter choices. And a wide variety of programs reduce to instances of streprogen programs. By that I mean you can take most popular programs that you find on the web, and you can formulate them as specific instances using streprogen. And it's forever open source and free. Here's what the output looks like if you choose to get a PDF. Here are some program parameters at the top, exercise information about the exercises, and you can see the weeks and what you're supposed to lift every single week for the entire program going down. Let's look at the code, because you have to write some code to make this work. This is how you create a simple program. This program is an 8-week program. It's rounded to the nearest 5 kilograms or pounds, whether you're in Europe or the US. It has 2 days, labeled day A and day B. And it has some dynamic exercises that are subject to the optimization routine. The start weights are given, and by default, we'll add 1% per week per exercise. But you can change that, of course. There's also a static exercise, curls, in day B, and that's just something that's repeated every week. So there's no optimization or anything like that. It's just a static string that's printed out. When I call program render, it actually does the looping through weeks and days and exercises and does the optimization. And then printing will give you a plain text output, but you can also get a PDF output. Here are some more program parameters on the program level. You can change the name, duration, repetitions per exercise, the range. If you don't want to work between 3 and 8, you can change that to, for instance, work between 1 and 5 repetitions. Percent increase per week. I believe the default is 1, but you can change it. If you're a beginner, maybe you can change it to 2 or something. If you're really advanced, you can lower it. Intensity is 85 here, and that corresponds approximately to 5 repetitions or something like that. And here are the 2 functions, the rep scalar and intensity scalar functions. These are functions that you define in the software, and the input is a week, so for instance week 2, and the output is a factor which intensity and repetitions respectively are multiplied with. So for instance, if the repetitions is 25 and the rep scalar function returns 0.8, for a specific week, it will take 25 multiplied by 0.8 and give you 20 repetitions for that specific week. You can change units and what you round to the weights. So in kilograms, that's often 2.5. Here's how you can create exercises. You can specify just the start weight, and the percent increase per week parameter will determine the progress. If you don't like that approach, you can specify start weight and final weights, and it will implicitly compute the percentage increase per week. You can change the percentage increase per week to be overridden for a specific exercise. You can change repetitions and the max and min reps for specific exercises, as well as set them on the program level. So to summarize, the features of streprogen are: you can use any duration, whether you want to plan for 4 weeks or 40 weeks. You can train 2 days per week or 4 days per week, whatever you want. Any volume or intensity and exercise, whatever you want. Many general functions for strength progression modeling are implemented. You've seen my law of diminishing returns function, obtained by solving that differential equation on the first slides. There's also the sawtooth periodization function and sinusoidal periodization function. I use combinatorial optimization to compute the optimal repetition schemes. And we've seen that as well. You give it intensity and repetitions, and it will give you the optimal repetition scheme for you to use. It's simple and well documented, but that's contingent on you knowing a little bit about programming. So if you don't know programming, you might have some issues, but you can go and copy and paste my code, and Python is not a hard programming language to learn. So I think you'll be fine. So it should be relatively easy to use. Of course, it's a bit challenging if you've never done any programming before in your life. You can export the program as a plain text file or HTML or a PDF. If you'd like to know more about this, then you can go to GitHub, which is where the software is distributed. There's an issue tracker. If you have any issues, you can post there on GitHub and I will reply to you. I've written a little bit more extensively about the theory behind these ideas on my own website. And there's a book that I recommend. It's written by Mark Ripto. It's called Practical Programming for Strength Training. And I think it's the best book for learning about these ideas. What I missed when I read that book was a mathematical underpinning and an implementation of all the ideas that he outlines. He outlines a lot of great ideas and some concrete programs, but I missed a mathematical foundation, and that's kind of what I've been working on for 7 years and trying to accomplish with this hobby project of mine. So I hope you liked my presentation. This is just skimming the surface of the algorithms and the theory and the implementation. You're welcome to go and use the code if you want, or you're welcome to go read that book if you want to learn more about the theory. Thank you so much for watching.